A big thank you to Brian Douglas for being the first guest on the Space Engineering Podcast. I had a really great time talking to him. And we actually did this twice. So the first time we had planned on only talking for around 30 minutes to an hour, but ended up talking for around 3 hours. And then the second time we talked for around 2 hours. So when I mentioned the first time we talked, that's what I mean in this episode. So this is a pretty long conversation, but I'll be posting short clips from both of our conversations for about the next 2 weeks. So be sure you subscribe and hit the bell button to stay up to date when I post these. And these short clips will be including all of these following topics from our conversations. So it's spacecraft attitude control, including actuators and attitude termination sensors like star trackers and magnetometers, Kalman filters, planetary resources, orbit determination, GPS, IMUs, Quaternions, Euler angles, simulations, including software and hardware in the loop, magnetic fields, PID controls, spacecraft modes, TLEs, orbit propagation, a little bit of relativity, Monte Carlo simulations, software engineering, including MATLAB, Simulink, C, embedded software. So there's a lot of stuff in there. So without any further ado, here is the first episode of the Space Engineering Podcast with Brian Douglas. So the first question is, so you had a pretty stable job at Boeing. I know you mentioned that your wife also worked at Boeing, so it wasn't the biggest risk in the world, but you decided to leave your job at Boeing to go ahead and go to Planetary Resources. So can you talk a bit about that decision process and kind of what made you, kind of what attracted you to Planetary Resources and how you went about that decision?
Yeah, sure. So at Boeing, I spent the first, I don't know, 10 years or so working space projects. Moved from California up to Seattle and started working commercial aircraft, which was still an interesting engineering problem, but it didn't hold my attention like space problems do, mostly on the exploration side of things. I liked building machines that were going to go to places that were difficult for humans to go to. So I don't know, I spent a year and a half or so working 737, 747 primary flight controls and was looking to get back into space. And it just happened to be good timing with Planetary Resources having their Kickstarter and being in the news everywhere and just being essentially down the street from me that I applied. One of the things that you mentioned, not a huge risk, everything felt like a huge risk at the time, or not really a huge risk, but you just don't know, right? You're going into some new scenario and you don't know how it's going to play out. In hindsight, it wasn't really that big of a risk. I had been sort of coddled, I guess, by big Boeing, with a very stable job and very slow moving engineering projects with long time horizons and all of that kind of stuff. And I didn't really know anything else. But it turned out, at least my experience with startups is that you are still a valuable engineer if the startup folds, right? You've learned a lot of things. You've got your technical knowledge, but with startups, you have sort of your business and your early program concept studies, and you just get exposed to a lot of stuff like spinning up labs that you may not have done otherwise. And so I felt like, in hindsight, just making that jump made me more valuable as an employee, and I could have gone back to Boeing or anywhere else afterwards. And so at the time, like I said, it's like an unknown event horizon. You don't know what's going to be on the other side of this line. It could be the worst decision I've ever made. But in hindsight, that's opened me up to taking a little bit more chances of starting my own company now, because it's like, I'll give it a shot, and if it doesn't work, I still feel like I've acquired enough information that maybe somebody will hire me. But so Planetary Resources was a space mining company. I mean, that was the goal. And originally we were building spacecraft, low Earth orbiting spacecraft, to sort of test out our hardware, test out our methodologies that we wanted to pursue, and how we wanted to build spacecraft as a team, which was a lot of fun. But the ultimate goal was to then do prospecting, which is to investigate potential mining spots in deep space at these asteroids, and then ultimately build mining equipment. That's the far out goal. So that whole string of long-term plans was just exciting to me. And so it was easy sort of to leave Boeing then at that point and go and do just something kind of wildly crazy.
Mm-hmm. So then when you first joined, you were in the ARCA 3 days. So that was the first CubeSat. And was that after the high altitude balloon days, or were you there at that
Yes,
time?
I was not.
Okay.
I'm post high altitude balloon.
Wait, so what were the mission objectives for the high altitude balloon? Because I don't really remember.
I don't know. I mean, I have like some theories and hunches, but that was before my time, and nobody really seemed to talk about it much afterwards.
Oh,
So
okay.
I don't have a good answer for you.
Okay. So then when you did come in, so ARCA 3 was the first 3U CubeSat.
Hmm.
And then you mentioned in the last talk that when you came in, it was decided that for the high level objectives and requirements that the spacecraft wasn't going to have any active control. So can you kind of talk about that decision of, just that whole requirement of not having active control and kind of why that was acceptable for that mission?
Sure. Yeah. Well, we didn't start that way.
Okay.
I mean, we started with having active control as part of the A3 or ARCID 3 spacecraft. The high level goals of that spacecraft was to rally around something that we could build a team, around. We could build. We could hire people. We could work on an engineering problem. We could build up our clean room, our engineering manufacturing processes. We could design our own hardware architecture from scratch. We could design our own software architecture from scratch, with the ultimate goal of saying that these are the first iterations of these things that we want to take to deep space, right? We weren't trying to build a CubeSat. We were trying to build a platform that would allow us to design and test out some of our deep space architectures that we were trying to come up with. And so that was the ultimate goal. And part of that was just figuring out what tools and processes and people we needed to accomplish that. And what does our team look like? And how do we interact with each other? What does the structure of responsibility look like? Because we're building up this team from scratch. We didn't have a lot of that, or at least we wanted to trade a few different options and practice some things by building real hardware so that we would be in a better position to then take the next step.
Mm-hmm.
So that was the main goal of A3. And part of the way through that process, we're a ride share, and the launch is going to happen with or without you. You don't really have a whole lot of say in that. And it got to the point where the launch was coming up and we weren't as far along with this full up design from scratch that we wanted, and there were some concessions that had to be made. And so the ADCS, the attitude determination and control system, that's responsible for determining attitude and pointing the spacecraft, ended up getting de-scoped from the project, which was kind of a bit of a running joke then from that point on, because the ADCS team then all of a sudden had a lot less pressure, and then it was like, oh, it must be nice to be the de-scoped people. But we were still proceeding in the background, building up our architecture and our algorithms and testing it, and our simulations and all of that stuff, so that we could be ready for the next launch. But the idea was that A3 didn't need to function as a spacecraft fully. It needed to be able to charge, collect power, store that energy. It needed to be able to communicate with the ground. It needed to be able to have all of its hardware architecture communicate with each other. And we needed to get data down from that. And it turned out we could do a lot of that stuff with a tumbling spacecraft for the most part.
So that did end up working, that you can kind of rely, after being launched into space with some random tumble, that you're able to do the things like communications and, if there was any scientific objectives like being able to image the Earth or something. So that was possible with that random tumble.
Well, the first part of what you said, for sure. I mean, you can set up a spacecraft to tumble. I mean, there's spinning spacecraft out there that are stabilized because they're spinning, and they're able, their antenna patterns are set up in such a way that they can communicate with the ground and they can charge. Their solar panels are set up, or maybe they're battery powered, but But yeah, you can absolutely set up a spacecraft to handle tumbling. Imaging the Earth is a little bit trickier. I mean, if you don't care what you're imaging and you don't care if
Yeah.
there's like smear in your image because you're rotating around, sure, you can take a picture, but that's not what A3 was doing.
Okay.
And A3 didn't have any science objectives at all. I mean, the objective was build a spacecraft as a team and launch it. No matter what the outcome was, the majority of our objectives were met when it launched,
Hmm.
because that was the whole purpose of it.
Okay, yeah. So can we get into that? How basically, as you said, the majority of the objectives were already met just by go ahead and building the spacecraft. But then, kind of, can you go into that experience of what it was like to watch it on the first launch, the first A3 when it blew up, and then the mindset of the team after that all happened, and also during the time, because that must have been a pretty crazy kind of experience.
Yeah, so our first Arctic 3 spacecraft blew up after, I don't know, 20 feet or so off the launch pad, which was surreal. That's the first time that's ever happened to me, but that's the first project, I suppose, that I was part of launch that wasn't some giant national asset, like that if it exploded, it would be, devastating. um, it was, yeah, it was definitely surreal, to watch that, and obviously disappointing. The thing with Arctic 3, though, it was going up as luggage to the International Space Station. It was going to get fired off of the ISS sometime later. So we didn't have, it's not like we were all in our command center, ground center, ready to communicate with our satellite and turn it on and start doing operations, because we were still months away from that, because it was just packed away. So I feel like it was a little bit less heartbreaking because of that, because we were there essentially having a party, because our spacecraft went together, it launched, and we've got a few more months still before we really have to buckle down and start operating this thing. Once it blew up, though, it was kind of a strange pivot for the company. Well, I don't want to say pivot, more of a split, because we had enough spare parts and we were already building up sort of a flight spare for Arctic 3. And so we were able to go off and do that and get that ready for a second launch. But again, Arctic 3 wasn't the end goal of Planetary Resources. And since we had already met the majority of our objectives already, the most of the team had to go off and start working Arctic 6, the 6U spacecraft, the next iteration, the one with more sensors and more actuators and more hardware and more technology built into that. So it was really only a handful of engineers. I wasn't actually even on the team building the second A3. I think it was just Hannah Goldberg and one or two others that were charged with put the flight spare together, get it ready to launch and go. And the rest of the team is going off and working on the next project already. So it was, I don't know, I guess it was a surreal experience, but at the same time, we had so much work to do that it was like, okay, on to the next thing now.
So how was, I guess, so what were the lessons learned from the A3 after the next time it launched, and that you took into A6, specifically to the ADCS side, so we can start getting into there?
Well, again, there wasn't much ADCS on A3. Ours was sort of a continuous evolution of our system. We took that opportunity, that time that we had, to really plan out our development schedule and what supporting equipment and supporting software did we need to generate in order to ensure that the system was going to be verified and validated throughout its life cycle, so that it was ready to go for A6. And so we spent that time building up a higher fidelity simulation, and getting like spherical air bearing tables, which is it's kind of like a really sad air hockey table, because it's just a post with a concave groove in it that air comes out of, and then a semi-sphere sits in top of it and allows this basically frictionless connection in 3 axes or so that we can place our spacecraft on top of and test at least some of the degrees of freedom in a frictionless environment. So we didn't, I don't want to say we didn't have any lessons learned from A3, because you're always learning stuff, but we didn't have those sort of big takeaways that we said, next time we're going to do this completely differently, because we didn't have an opportunity to test anything out on A3. Mm-hmm. There were some takeaways from the larger spacecraft, which was that power generation and communication, while possible to be done, while it's possible that you can do that with a tumbling spacecraft, it is not guaranteed. There are some pathological cases in the spin axis of the spacecraft where you could get into these situations where you're not charging at all for long periods of time, and you can't get out of that, or you can't communicate for long periods of time and you can't get out of that. And so we knew that we needed some form of rudimentary control, even if the main spacecraft computer never turned on or didn't work whatsoever, that we wanted to be able to control the attitude of this spacecraft, even with just some of the smallest, edge compute elements that exist, these distributed compute elements that exist throughout the spacecraft.
So can we go deeper into that, to the distributed compute elements? So
sure.
So in general, I would imagine that when you design a control system, that you're going to have the main computer actually doing all the calculations and then sending the commands to, say, your reaction wheels. But you say that you guys built kind of a fail-safe system, sort of, where if the main spacecraft computer went down, just these other compute elements could also just do some sort of rudimentary, so maybe just point at Earth and point at Sun. So how did that,
Mm-hmm.
how did all that work out?
Well, it worked out great. in the end, it was really difficult to get all of these compute elements working together in the way that we've architected it, but that's a different story. From a controls perspective, when the main spacecraft computer was operating, it was doing the bulk of the ADCS calculations. It was doing the path planning. It was doing the state estimations. It was doing the actual controller itself. It was doing all of the mode logic and everything. It's what you would kind of expect, which is go out there, collect all of the sensor information, give me the sun sensors, give me the star trackers, give me the accelerometers and the magnetometers. Let me get all of that information. I'm going to filter it, rotate it all into the control coordinate system. I'm going to throw out any data that I don't trust for whatever reason. I'm going to estimate the state of the vehicle. I'm going to determine where I want to be compared to that estimate. And then I'm going to drive the actuators to close that error. And then the actuators are torque rods in our case, or reaction wheels. So that's all what you would expect. The difference is that our what we call device managers, the software element that would manage the actuators and manage the sensors, they did all of that on their own distributed compute element. And these compute elements are really weak. I mean, they're the types of microprocessor that you might have in your watch, for example. I mean, just real tiny things. And all their job was to generate telemetry from these nodes, like the reaction wheels, run the reaction wheel motor controller. So the main spacecraft computer would say, reaction wheel spin up to 1,000 RPM. And then the smaller compute element would take that and adjust the current and voltages to the wheel to control it to 1,000 RPM. So the motor controller was down there. And So it distributed some of the low level commanding and messaging and things like that to these distributed elements. And that was our architecture. The nice thing about that was that it was modular, so we could remove a reaction wheel, and we didn't have to change the flight software very much, because the flight software would understand that there wasn't a node there, and therefore it's not in the design. What that ended up allowing us to do is, if the main spacecraft computer died, we were thinking, well, we still have a computer that can talk to the reaction wheels and control its RPM. We still have a computer that can read the sun sensors. We still have a computer that can read the IMU and all of these things. We just don't have the big brain to process all of that information, all that data, and come up with the calculations for the actuators. So we added another low power small computer whose sole job was to communicate with all of these other distributed nodes and do the most basic control, which was figure out where the brightest object was that it could see, like look at all of the photodiodes and the sun sensors and say, where do I think the sun is? And then move the reaction wheels in such a way that points the solar panels towards the sun. Like, it doesn't know where it is in orbit. It doesn't know hardly anything. It's just a bare bones controller that can operate on a bunch of these little low power compute elements distributed throughout the vehicle.
So going off of that, I want to learn a little bit about the actuators that you use as far as in the trades. So was it, as far as a 3U CubeSat, was it a bit obvious, or how much trade was there going into choosing, I want to use reaction wheels, and then in order to desaturate, I want to use torque rods, magnetic torque rods?
Mm-hmm. Yeah, well, I mean, at some level, every decision you make is a trade. And sometimes it's a no-brainer, and you do that trade really quickly in your head. You're like, do I want thrusters? No, and then you move on. So for some of that, that's what we ended up doing, right? We didn't do a lot of formal trades at the beginning to determine reaction wheels. We knew that we didn't want thrusters, because thrusters on CubeSats and adhering to the CubeSat spec with them and everything it's just more complicated than we wanted. And we were going to be developing our propulsion system for later, larger spacecraft. So we didn't want to mess with that. So reaction wheels were the natural choice for managing our momentum. There's CMGs, the control momentum gyros, but typically those are for these high torque applications. They're a lot more complicated mechanically and electrically, and it's just not something. I'm not actually sure if anybody's built them with CubeSats. That maybe they have, but I'm not aware of any CMGs on CubeSats. So reaction wheels were the obvious choice. And the trade came in, what do those reaction wheels look like, right? Do you want 3 wheels? Do you want 4 wheels? Do you want 5? How much momentum do they need to store? How much torque do they need? What is the physical volume that they have to fit within? And that's where our trades really took off, is once we've decided on reaction wheels, we started going down the path of what orientation do all of these wheels need to be in, how much momentum do they need to store, how agile does the spacecraft need to be, and so on. Now, reaction wheels are a momentum, like they transfer momentum between the wheel and the body of the spacecraft. And so when the spacecraft starts to absorb momentum through external forces and torques that are coming in from the space environment, and it starts to move the spacecraft with that external torque, the reaction wheel spins up in the same direction to absorb that momentum and keep the body of the spacecraft fixed. The problem is you can't get rid of that momentum without interacting with that external world again, because that momentum came in from the environment, from the space environment, and you have to shed it back to that environment. So over time, as momentum builds up in the spacecraft, the wheels tend to get faster and faster and faster and faster, and eventually you're going to saturate them. You can't go any faster. And that's when you have to figure out how to desaturate those reaction wheels, or desat them, or dump momentum, depending on what you want to call it. And how do you do that? Well, you could fire thrusters to do that. You could push on the Earth's magnetic field with torque coils or torque rods. You could jettison a large part of your spacecraft, potentially. I mean, anything, right? In some way, you need to interact with the external environment. And since we knew we weren't going to have thrusters, we needed magnetic torquing capabilities. And torque rods are a much more efficient way of generating a magnetic field than a torque coil. They tend to take up more space and they're heavier. But if you care about power over mass and volume, they're basically the way to go. So that was sort of our decision-making process for why we ended up with torque rods and why we ended up with reaction wheels.
And then, so going from the attitude control to attitude determination, so what were the decisions there? Because from what I remember, star trackers are like really accurate and seem to be a pretty good solution to do attitude determination along with other things. Like, I believe, if I remember correctly, I think there were magnetometers on A6. So what were what was that decision process as well of doing the trades of how are we going to do attitude determination?
Yeah, well, I mean, usually it starts with some requirement. How well do I need to point? And then you decompose that into, into subsystems and all of that stuff, and you come up with some value that you said, I need to know my attitude to this degree. What sensors are available that allow me to do that? And not only do I need to know my attitude, but I have to be able to determine my attitude when I'm in eclipse, and any number of things. And so that's usually where you end up with your sensor suite. For us, we didn't actually have very stringent pointing requirements for A6. We needed to be able to point the solar array towards the sun, and we needed to point within, a half a degree or so towards the Earth, or whatever it was, which is, doable using the magnetic field of Earth and using the sun, for example. We knew going in, we needed star trackers later on. And we knew that we were, this ended up not coming true, but we thought we were going to be building dozens of spacecraft. And so it's cost prohibitive to go out and buy star trackers, at least it was for us, knowing that we were going to need dozens of them or more going forward. So we're like, we knew we needed to develop our own star tracker. So that was an objective of A6, which was to develop this star tracker and test it on this platform as part of our future goals of going into deep space. So we sort of, we had a bottoms up kind of approach to engineering there. We didn't say we needed a star tracker because we had to meet pointing budgets. We needed a star tracker because we said we needed one.
Okay, so can you explain a little bit more how star trackers work? Because from what I know is that they have an internal catalog. So basically they take a picture of whatever they're seeing, say the sky, and they have an internal catalog that they then kind of have to figure out, okay, if I see these stars, I have to guess that I'm in this orientation. So can you go a little bit deeper into kind of how they actually work?
Yeah, I mean, you've got the basics down. The details are all a little bit different by algorithms. But basically, they take a picture of something. Sometimes the moon's in there, the sun, the Earth, hopefully not. Hopefully you're pointing somewhere into deep space, and you get back a mostly black picture with some, bright dots throughout it. And let's assume all of those, for now, let's assume all of those dots are stars. You would then have some kind of algorithm that would go through and scan through that whole image and determine what it thought were bright enough points to be labeled stars. And then it would label all of those stars and say, I think I've got these 6 points here are stars. Then there's another algorithm that's essentially doing a pattern matching between those 6 stars and what it already has in its star catalog of 1,000 or 2,000 or 10,000 stars or whatever it is that you need in order to be able to determine your attitude in 4 pi steradian space to the degree that you want. So you want your smallest star catalog possible because it costs a lot of CPU time to do that pattern matching. So you don't want to pattern match through 100,000 different stars, for example, if you don't need it. That's just sort of wasteful. Now, how they do that pattern matching, they all do them differently. You can build like triangles between sets of 3 stars, and you can characterize that triangle in some way, either by the 3 lengths or an area or something like that. And then you can quickly look through the triangles in your catalog and see which ones have the same ratio of those 3 lengths, and then how many of those can I match in one scene so that I can get more and more confidence that I'm actually matched the right pattern. Now, it seems easy, but it's really, it can be really difficult in certain situations because cameras are sensitive detectors, and they're sensitive to like deep space radiation and all sorts of other hazards of space. And so over time, you start to get hot spots, and dead pixels. And so what, was a nice clean image at the beginning of your mission now has a bunch of what look like fake stars peppered throughout them. And you can then start mapping those dead pixels with like a pixel map and subtract those or take them out over time, and you're building up that map. There's a lot of sun glare, the sun coming in at some side angle. If your baffle isn't designed properly or isn't large enough, you get a lot of glare and glint across your screen. The Earth is in the way, the moon is in the way, and it's easy to get confused as to what is a star and what is not a star. So building a camera that can take a picture of the stars is a relatively trivial thing. Building one that can operate in space and to the degree necessary so that your algorithms can actually pick out stars in the image is tricky, and it takes a lot of people a lot of time to get that right. So more often than not, if you're only using 1 or 2 or 3 star trackers in your project, it makes a lot more sense to buy one that somebody else has already gone through all of this effort of verifying and validating and just running with it than designing your own. It's not like a photodiode or something that can be done relatively simply.
So then what is the, I don't think this is a trade, but how much do you rely, this is, the question that I want to go to is towards Kalman filters. So how much do you rely on, say, a star tracker versus a magnetometer as far as being able to determine your attitude? And also, does it matter at what point in the mission you are? Because as you said, things can happen to the camera where it can make it less reliable. So yeah, so does that change over time, and how does that whole process go of determining how much I trust one sensor over another?
Yeah, so I mean, there's the general idea of Kalman filtering or like statistical estimation that I don't know. I could talk on this forever. I don't want to take too much time, so I'm gonna relate it back to what we did on A6, for example. So in a Kalman filter, you have a mathematical representation of your system, a mathematical model in the form of state space equations or something. And using that model, you are predicting future state. You're estimating what the system is doing over time without looking. And it would be like similar to being in your bedroom, closing your eyes and walking to your kitchen. You have a pretty good understanding of the map of your house. And because you can feel how you're walking and moving, you can estimate where you are. But the longer that you're estimating where you are, the less certain you become in your accuracy. I think you can easily walk straight out of your bedroom door without running into anything and being fairly confident. But now if you did you turn 90 degrees or a little bit less? I don't know. And you walk a little bit further and a little bit further. And eventually this estimate, you trust less and less and less, right? And that's what this mathematical model is doing for us, is it is essentially saying, well, I was rotating at this rate and in this direction before. So in 1 second, I should be whatever, a little bit further. And I've estimated that. And 1 second later, I should be a little bit further. And the longer you go predicting and estimating your future state, the less confidence you have in it. So then occasionally, let's go back to walking across the house. You get halfway there and you're like, I feel like I'm going to hit a wall. I'm just not confident that I know exactly where I am. Let me just open my eyes real quick. You reorient yourself. You're like, here's where I am. And then you can close your eyes and keep walking. And that's essentially what we're doing with a star tracker, is we're opening our eyes occasionally and saying, where are we actually? And then the Kalman filter combines those two estimates, the one that we predicted with a model and the one that we sensed using a sensor. With the case of your eyes are probably pretty accurate, so you would trust them a whole bunch when you reorient yourself, unless maybe, you wear glasses, you don't have your glasses on, it's like a fuzzy world, right? You may have some error in your sensors. Well, on our spacecraft, we do have errors. The star tracker isn't perfect, our estimate's not perfect, and the Kalman filter is a way to blend these two imperfect estimations, one estimated from a sensor, one estimated from a model, blend it together to get a good state estimate. Now, how that estimation, well, not how it's done, but how much do you trust your prediction and how much do you trust your sensor? You can bake into the Kalman filter ahead of time by knowing how good you built your model and by knowing how good your sensors are. But in the case of star trackers and other sensors that degrade over time, you can change how your sensor noise, like how much noise there is in the sensor real time. So with a star tracker, I said, like, if you can see 4 stars, that estimate is not going to be as good as one if you can see 16 stars. Imagine 16 stars and you can match that pattern into your star catalog. You're going to have a lot of confidence that you're looking at the right thing. And each one of those errors of each of those stars is going to kind of blend together and RSS, root sum square out of there. And you're going to have a better estimate of where you're pointing versus 4. So the star tracker comes back with its own guess as to how good it's doing based on how many stars it sees and how fast the spacecraft is rotating. Because you can also imagine that when the shutter is open on this camera, if the stars are sort of streaking across because you're rotating, you don't have these nice point stars. You now have these streaks. And you think, okay, well, I can still centroid on that streak and say it was in the middle of that streak. But were you rotating at a fixed rate? If not, then it's not the center. So rotating a spacecraft while doing star tracking decreases its error. So you can take all of that information and then how long you've been, operating, like 1 month later, 3 months later, 4 months later, you might start to degrade your sensor just because, like I said, with these hot pixels and dead pixels and stuff. So you can take all of that information and you can put that into your Kalman filter and say, this is how much I trust my star tracker. And this is how much I trust my model. And this is how much I trust whatever other sensors are going into it, my magnetometers or whatever. And the beauty of a Kalman filter is that it takes into account all of those statistical distributions and comes back with an optimal estimate given all of that information. So as long as your information going into it is accurate, what's going to come out is the optimal estimate that blends all of those statistical uncertainties and everything.
So the process sounds more involved than what I originally thought for star trackers. So how does that, so I want to get into flight computers, and I know you said you don't know too much, but I still think you know more than most people. So how does the process of picking a flight computer, so how much compute power do I need? What kind of clock speed do I need in order to be able to make all these calculations in real time on board the spacecraft? So how does that process go of picking a flight computer?
Yeah, well, let's stick with star tracking for now. And it's not straightforward. It's not like you can sit down and say, this is how much processing I need to be able to do. because there's trades in everything. The algorithm that you choose to do pattern matching can vary in how many operations it takes wildly, right? And the result could be that it is you can have a slower processor with less memory and have a less accurate result, because you need to do your star tracking in 1/10 of a second. So just get me whatever you can in 1/10 of a second. That's all I have, like, for example. So there's the algorithm side of things, there's the flight software side of things, and there's the requirements on pointing. Like, maybe you need a star tracker to update 100 times a second because it is your only attitude sensor and everything else runs at 100 hertz. So I better be getting measurements back from my star tracker at 100 hertz. Otherwise, I don't know where I am, let's say. Versus my IMU, my inertial measurement unit, and the rate gyro built into it is really accurate. And I can dead reckon using just the IMU for an hour before I start to break my pointing budget. In which case the star tracker can be turned off, because I'm just going to predict where I am over time. I'm going to use that mathematical model, and I'm going to predict where I am over time using my IMU. And then once an hour, I'm going to wake the star tracker up, take a picture, and it can churn on that picture for 10 seconds because I don't really care. My IMU is amazing. And then it's just going to turn slowly for 10 seconds, return a quaternion, or an attitude estimate. And then I'm going to fold that into my Kalman filter, and I'm going to estimate new state, and then turn the star tracker off, and then just keep going. And all of these things are interrelated with each other. So it's this big swirl of how good is my algorithm, what are my requirements, and what compute processors exist, and what can we get away with. Now, for A6, we weren't. This is why I say I don't know a whole lot in this side of things, is because ADCS. When I say we, I mean ADCS didn't drive the selection of the processors. Those processors, because they existed, some of them existed as a carryover from A3, and the architecture already existed. We had to find a way, for the most part, to fit into the box that was already created for us. And so we had to use the resources that already existed, and we had to adjust our requirements in some cases, but we had to adjust that trade between how good does our algorithm need to be, how good does our IMU need to be, because our flight computer can only do so much for the most part.
So you mentioned quaternions, and I want to get into that because, first of all, I think quaternions are super interesting, and then you can get deep into the math where it's kind of just really crazy. But one thing that I'm struggling with, and I kind of want to get your guidance on, is that I'm currently working on making a video about Euler angles, and I'm a little bit struggling to find out, because I know mathematically this is how you use them, this is how you describe one reference frame with respect to another using Euler angles. But how did you use, and in general, how do you use Euler angles, or if you do, for spacecraft attitude control, for doing analysis on a control system, and also that versus quaternions, and then when do you do one versus the other?
Yeah, so quaternions, which is using 4 elements to represent a rotation between 2 coordinate frames. So that's what we're talking about here. We're talking about a rotation. Is a very, there's a lot of benefits to using it within flight software. You don't have the gimbal lock problem. You don't have 9 elements that you have with a direction cosine matrix. You only have the 4, so it's very compact. And you can set up a multiplicative Kalman filter to do all of your attitude estimation with quaternions and all of that stuff. But they tend to be a lot harder to visualize and understand. And so we did all of our processing with quaternions on the flight software, but then we did all of our visualization well, not all of it, but the majority of our visualization in Euler angles. So when we determine how, just we're looking at a time history of pointing, for example, more often than not, we would convert that into something that we can look at and make some sense of. Even if it was, we didn't have to do this, but even if it was like a small angle approximation, which is, as long as, like a no rotation of a quaternion is like 1, 0, 0, 0, assuming the scalar is first, then as long as the rotation off of that is really small, all of those 3 numbers after the 1 is all really, really small, you can just take those and, can't remember it off the top of my head here, but like double it, and those are the radians in Euler angles, approximately, something like that. You could get a sense of how things are progressing in your control system very quickly just by looking at it that way. So I agree, like Euler angles, degrees, those types of things are much easier often for humans to interpret, but we wanted to keep everything consistent within flight software. So there's no reason to use degrees within flight software for us. There was no reason to use anything other than quaternions, because the computer is interacting with itself there. The software is interacting with itself. Only as an outsider, when I command something, we may want to command it in degrees, possibly. We may want to view it in Euler angles, possibly. All of that stuff are sort of wrappers that we would put, or post-processing algorithms that we would put outside of flight software. Everything within flight software is consistent with units that are set up for the algorithms themselves and not for people to interact with them.
So putting you on the spot a little bit, is there any way, do you think, that you could intuitively explain quaternions? Because I think they're super interesting, and just, the fact that they're 4-dimensional imaginary numbers is kind of crazy. So yeah, do you have anything that you use in your head that you kind of, for yourself, just intuitively, just what a quaternion is?
Well, like a quaternion, the specifics of how those numbers come about can be a little bit mind-bending, but I think in terms of angle axis, like representation makes a lot more sense. So the craziest thing about angle axis, in my mind, is that you can describe any rotation. Like if I have my phone here, I can get from this orientation to any other orientation by rotating along a single well-defined axis. So I can go from here with this vertical axis here and rotate around it this way. I mean, that makes a lot of sense. And I can rotate it around it this way. But if I rotate it around some crazy angle off to the side, it's going to do some kind of weird flip and it's going to end up somewhere. So the key to angle axis is that some axis in any direction, and if you define that axis and you rotate around that axis some amount of radians, you can get to any other rotation. So that's sort of the key behind it, and the intuition behind that is lost on me right now. I wouldn't know how to explain like why that's the case, but if we go in with that assumption that that's the case, things start to make a lot more sense. So now, instead of Euler, where you're saying rotate first in this axis, then in this axis, and then that axis, instead of doing 3 rotations, you're only doing 1. And you're doing 1 rotation around some axis that's really strange, like some weird direction. And that's it. So now you can find that axis, determine how far to rotate along that axis, and you got your 4 numbers. The axis is defined by 3 of those numbers. And then the angle around that is defined by a 4th number. But now you have to say, like, well, that's not quite what a quaternion is, because a quaternion is like normalized to 1, and they have all of these weird mathematical rules. But essentially, the underlying concept of a quaternion as it relates to rotations is that it's an angle and an axis. And then some math is done to package it into the quaternion form so that whatever it is, like I squared equals J squared equals K squared equals I times J times K equals -1, or whatever that is, that I can't remember off the top of my head. But there's some sort of logic to it. But the other thing that helps is that just like an imaginary number is a 2-dimensional number, a quaternion is just a 4-dimensional number. It's just, 4 dimensions, and each dimension represents something akin to an x-axis, a y-axis, and a z-axis component, and an angle, a scalar value around that axis.
Okay. Yeah, that makes more sense, because when you do a principal axis and rotation, those are 4 values, like you just said. So it's kind of similar in a way to the quaternions.
And if you do a principal axis rotation, it makes sense in quaternion world too. So this is let's say this is 1, 0, 0, 0. And I don't know, I'll say that this is the y-axis.
Okay.
So if I rotate whatever 90 degrees, then it becomes 0, 0, 1, 0. Like that 1 is in the y-axis point. I did a max rotation in one direction in the y-axis. That didn't help at all, I'm realizing. But if you start using them enough, you can kind of, I'm not there yet. I mean, some people can look at quaternions and I feel like they just see it. Certain rotations I can look at and be like, oh, okay, I kind of get it. But they are useful, and I guess that's why we use them.
So then I also want to get into simulation, and specifically soft sim. So I guess, first of all, can you give a brief explanation of what soft sim was at Planetary Resources?
Yeah, so spacecraft are difficult. Actually, most engineering projects are difficult in the sense that if you want to test them in the physical world, it is expensive and possibly impossible, right? If you want to test a car in the snow, you're going to have to go somewhere where there's snow and hope there's the right snow and all of that kind of stuff. And physical testing is absolutely critical and necessary, but a lot of testing is done in a simulated environment. And especially when that physical environment is impossible to get to, like 0G or microgravity of space, low friction and all of that stuff. So we built simulators like everybody does, that simulate the physical world that we can test our ADCS system within. Soft sim was a larger simulation environment that allowed not just the ADCS system to operate, but also the rest of flight software, like the actual flight software to operate in this simulated environment. And it had things like antenna pattern models and solar generation models and all sorts of things. So we could build up these simulations running the actual flight software and determine how well the flight software does and how much power it's going to generate. And we can switch between spacecraft modes and do all of that stuff, like a day in the life style testing. So kind of in a nutshell, that's what soft sim was. Soft sim was this way to programmatically determine which elements we want in our simulation and then run a simulation with flight software in the loop.
So then with the software in the loop part of it, can we go into kind of the hardware in a loop as well? Because we talked about this last time, but if you could go over this again, kind of the spectrum of what hardware in a loop simulation is and then how it is useful.
Sure. So I think I said this last time also, but there's a quote that I like, and I don't remember who said it, but the best simulator in the universe is the universe itself. So and there's also this other saying that people like to throw around, which is like all models are wrong, but some are useful. And a model is just a representation of reality, which is all a simulation is that you've got a bunch of models of reality, and they're just imperfect representations. And so you can easily convince yourself that your system is working if all you're doing is running it in a simulated environment. And this environment is not quite matching reality. And so you say, oh, everything is working perfect in my simulation, but then you go and put it on the target hardware and you go fly it in the actual environment and nothing works. So because of that, hardware testing is critical, right? And we do a lot of hardware testing, like thermal vacuum testing, where we test the entire spacecraft in a thermal environment and in a vacuum to make sure that, you know, heat transfer and all of that stuff is working properly. But there's things in between those two, of like a purely simulated environment and a purely physical environment, is that you'd like to combine those two in some way. And there's like a spectrum of what that looks like. You could have the full up spacecraft, you know, sitting on a table, thinking it's in space, but interacting with a simulation of the environment. So what happens then is, you know, the IMU is measuring Earth rate because it's just sitting on a table, but you cancel out that message and you say, no, don't trust the real IMU. I have a simulation of an IMU here, and my IMU says that you're flying around the Earth, and so you're rotating at a different rate. So let me insert that different message into that that path, you know, override the IMU, and now the spacecraft sitting on the table thinks it's rotating. And so because it thinks it's rotating, it says, oh, I need to move my reaction wheels. So then the reaction wheels on the table start spinning up, and your simulation, you know, intercepts those reaction wheel commands and says, oh, they're spinning up the reaction wheels. Start adding torque into my system in the model and start rotating the spacecraft as though the reaction wheels are really affecting it, which then affect the sensors, which then go back into the, you know, the satellite sitting on the table. So in that way, you get sort of the best of both worlds, in that you have control over the environment and you can inject faults and you can put it in situations that are difficult to test, but you have the actual flight software running on the actual hardware, interacting with the actual battery, potentially sending commands to the reaction wheel and the other devices, and you can see all of that, and you can see the reaction wheel spin up, and you know, all of that kind of stuff. It's a good not compromise. It's a good set of tools that you have at your disposal to do engineering, which is allow the real hardware to interact with simulation and simulated models. And you can take that, like I said, in a spectrum. You could do what I said right there, which is have the full spacecraft with a simulated environment. You could just simulate, you know, the rest of the spacecraft and flight software and everything, and have it hooked up to the real reaction wheels because you want to see how the reaction wheels are going to react, for example, or something. So it's a way to combine models and simulation with the real physical hardware, so that you don't have to rely on a imperfect representation of that hardware. You can get the actual hardware operating in the real physical environment.
And can you talk about, because you mentioned this last time, that one big mistake that Brandon found, where you had the polarity issue with the control system? Yeah, so can you talk about that, kind of, first of all, how he found it, and then just how he found it, and kind of, I guess, if you had maybe a lesson learned, I don't know what lesson you would have learned besides like put a negative sign maybe. But, yeah, that whole process.
For sure. So first off, we're talking about Brandon Block, who was a member of the ADCS team, GNC team at Planetary Resources, and all around superstar engineer, by the way. I'll have to just throw that out there now. One of the troubles with designing your flight software against a model, and what I mean by that is like model-based engineering, where instead of designing your control system on the actual physical hardware, and you know, and you're getting feedback right there, you build a model of your hardware, you build a model of your environment, you trust that model enough to go off and design your flight software against it. In our case, our attitude, determination, and control system. So we're going to design our flight software using this model of everything. And the hope is that that model is good enough that when we take our hardware, our software, and we put it on the real physical hardware, it's going to work well enough. And maybe we'll have to tune it a little bit, but for the most part, it's going to work well enough. Well, the issue came where I I built a magnetic model of the Earth, and I built a flight soft and a magnetic magnetometer, or I'm sorry, a torque rod model in our simulation. On the flight software side, I wrote a control law that would detumble the spacecraft. And basically what that is when the spacecraft is rotating, you can measure the Earth's magnetic field and see that the Earth's magnetic field is rotating because it's relatively fixed over 10 seconds or so in orbit. So if the Earth's magnetic field is moving relative to the spacecraft, you're the one doing the moving because the magnetic field's not moving. And so because of that, you can fire these torque rods at the exact right time to push against Earth's magnetic field and slowly slow the spacecraft down and detumble it, and basically get it fixed relative to Earth's magnetic field. And it worked great. It was quite amazing. All of our simulation runs, everything looked good. And the problem with this particular set of actuators is that it's extremely weak. These torque rods produce very, very, very little torque, not a noticeable amount of torque that we could put this thing on an air bearing table and see it move. There's just no way. So the only way to really test it is to, put an external magnetometer against it and say, yeah, it's firing in the right direction and all of that kind of stuff. And I had convinced myself that it was all set up correctly. And in an audit, and I don't remember the specifics of why, I think Brandon was just going through and double checking things because we were, a couple months away from delivery, found that there was a polarity issue or a negative sign flip on both the flight software algorithm, the controller doing the detumble, and on the simulation side. And so those two negatives canceled each other out. And so in the simulated world, everything worked perfect. And in the physical world, it was still firing the torque rods, but since they weren't producing enough torque to see, we couldn't tell that they were in the wrong direction. And I had done the calculations, and they said it was the right direction. Brandon redid the calculations and said that they're not in the right direction. And we sit down and he was right. And it would have been essentially mission ending, because instead of detumbling and slowing down the spacecraft, it would have just been getting faster and faster and faster because it would have been pushing the wrong way against Earth's magnetic field. So that was a mission-saving find that he found, and it, I'll forever be grateful that he found that when he did. But that's sort of kind of the moral of that story is like, it is easy to design bad flight software that looks good if you're designing it against a bad model, because the two things, you're going to design one to that model. And so the whatever errors you have in the model, you are going to incorporate and cancel out perfectly in your flight software. And so it's really critical that some amount of validation and verification of the model is done against reality before you spend a lot of time building up your system using that model.
So one thing I remember that goes along the lines of you can't really, or it's hard to model in simulation, is that as far as the avionics go, there's sometimes where the magnetic field that is caused by a current can actually mess with the magnetometers and what they're seeing. And I think if I remember correctly, when I was there, I think third summer, we were taking a look at, or Krish was having me take a look at kind of how, when the spacecraft heaters were on, so that current, because there's a lot of current, that they was messing with the magnetometers and then was then messing with the attitude determination system. I don't know if I remember that correctly, but I think this goes into flat sat and kind of what a flat sat could do. And is that the kind of mistakes that you would want to catch, or you could catch from a flat sat simulation? Or I'm not sure what the question is there, but I
okay. Well, first off, you mentioned Krish. This is Krish KC, also a member of the ADCS team, also superstar engineer. One of the things I lucked into at PRI was that the team was amazing, and that was mostly done before I even got there. So that's why I said lucked into it. But yeah, so let's imagine this. A magnetometer is not measuring Earth's magnetic field. It is measuring a magnetic field. And coils of wire generate magnetic fields when current runs through them. And some metallic structures bend magnetic fields when they pass through them. They change the direction of them in some way. And permanent magnets, like those in motors, like those in reaction wheels, have their own magnetic field. And so now you've got moving magnets on a spacecraft in the terms of reaction wheels. You've got coils that are driving high currents through them, and those are dynamic. So like when the solar panels are charging, a lot of current's going to be going through that sort of power bus to the battery, and that's going to generate some kind of magnetic field. And then when that stops, it's going to go away. And then you've got metallic ferrous structure on the spacecraft that's going to bend the direction of Earth's magnetic field. So all of that is working against you, because that's what you're actually measuring when you're measuring something with a magnetometer. And that is something that is very difficult to predict ahead of time. Like maybe if you had a really amazing model of your spacecraft and all of the electromagnetic fields and forces and everything like that, you could predict it ahead of time. But for the most part, I'm not sure of anybody that does it that way. What we did is we characterized the vehicle after the fact, and we set ourselves up with some requirements that said we need to know the magnetic field of Earth to within some value, plus or minus, some statistical, deviation, so some sigma value, and then that set a requirement on how well we had to calibrate our system. So it became a calibration issue after the fact. And there's a couple ways that we tackled it. One is just calibrating what's called the hard iron and soft iron sources in your system. The hard iron are the things that generate magnetic fields, like permanent magnets and coils. And then the soft iron are the things that just affect magnetic fields. So those are the ferrous materials and stuff on the vehicle. And to oversimplify this, you just take your spacecraft in a fixed magnetic field. So either the Earth's magnetic field, if you trust that the building you're in is not affecting that, or in some sort of like Helmholtz coil where you have control over the magnetic field. You take it and then you rotate it in all 4 pi steradian directions, and you can build this calibration matrix from that takes care of all of that stuff. So we did that for sure. The problem is some of those sources are dynamic, right? They're not static. Sometimes you're charging, sometimes you're not charging. Sometimes you've got some high power compute element on that's pulling a lot of current, and for whatever reason, the path that current takes does some kind of a loop. It's not like a straight shot somehow. So the other way to do that is to schedule different calibration coefficients based on the mode of the spacecraft. So we would do that 4 pi steradian thing with the spacecraft completely off. And then we did that again when it was on. And then we did that again when it was charging. And if they varied greatly between any of those modes, we had to schedule a switch. So whenever the spacecraft would go into a different state, like a charging state, we could switch to a different calibration set for the magnetometers so that we could take out that particular interference, magnetic interference.
Could you real quick explain the steradian? Because I think that was a term that I never heard before planetary, that it's kind of like an angle in 3D, if I remember correctly.
Yeah, it's a 2-dimensional angle. So like a radian is a 1-dimensional thing. It's like an angle. And a steradian is, I'm going to get this wrong because I just used the term. I haven't really defined it, but it's essentially like an area of a sphere. So instead of a circumference of a sphere, it's the area of like a spherical shell. And so you want to say like 4 pi steradian is the entire spherical shell, like all in all directions. That's the area of a sphere.
Yeah, that's kind of what I remember. And so one thing, going back to controls, I was wondering because you can implement and design a really complex and a really good control law on the ground. But going back to the flight computers is that sometimes you're limited on compute power. So are there cases and or trades where you kind of have to use a simpler control law, say for the ADCS, than you would like to say on the ground because you have more compute power?
Oh, I mean, sure. I mean, it's it's like the statement, how much data do you want? Well, I want all the data. And eventually you're going to run out of bandwidth to send that down, and then you have to start making trades, right? You want everything to be as best as possible from an engineering perspective. From a practical perspective, you want to meet the requirements and just meet them. Like, you don't want to exceed them because you're robbing from somewhere else that needs that, right? You're almost always on the edge of infeasibility across the system for the most part. It's like a give and take. So what? Well, let me answer a slightly different question, if that's okay.
Okay.
Which is, more often than not, my decision on the controller that I'm using doesn't come down to the compute power. But this is just the projects that I've worked on.
Mm-hmm.
Not in general, this isn't a general statement, but they don't come down to the compute power. They come down to, how am I going to convince myself and my colleagues that this is going to work? And if I do a PID controller and I say, look, I'm modeling my system as a linear model, and here is why I can do that. It's very straightforward. Look at how close this linear model matches the real system. Now that I have this linear model that we all agree is okay, here is my PID controller that I designed using that linear model, and look how good it works. And there's a whole bunch of metrics and things that we could look at to show that it works well. And people understand it, and people understand PID, and they understand, like, oh, what all of those gains are doing, and it's a very simplified thing. And so it is easier to convince yourself across the entire state space sometimes that controller is going to work, and it's easier to convince other people. And whenever you make a change to your system, it's relatively straightforward to retune the controller, this PID controller. And if you have to go into the field and tune your PID controller in the field, each of those three gains make some amount of intuitive sense. So that's nice. Mm-hmm. But I could get better performance if I do H infinity, or, you know, maybe some form of LQR or something like that. But let's stick with H infinity. I can come back with this like 12th order control law with a whole pile of numbers that each individual number doesn't make any sense on itself, but it works really well, you know, and it works. I have all of this data to show, look how good it works. But it's really susceptible to the model, more so than, you know, more so than like PID is for you. Like, you can design robustness pretty easily in PID. And so with H infinity, you say, well, I want it to be robust. So now I want to make sure that I've designed into my model a bunch of uncertainty. Like, which parts of my model don't I trust, and how much don't I trust it? So now I have this uncertain model, and now I can design like a mu synthesis controller for it. And it's going to come back and it's going to be like 20th order, and it's going to be crazy. And I'm going to show, like, look, as long as all of these error bounds, you know, the error stays within these bounds, it's going to be good. It's just, it would be harder for me to convince myself, because it has so much reliance on the model then at that point. To convince myself, it would take more effort to convince myself that it's actually going to work on the real hardware, and it's going to take a little bit more effort to convince the rest of the team and management and all of that kind of stuff. And then the other downside is that the controller now doesn't have three nice, neat, intuitive numbers. It's got dozens of numbers that don't really make any sense. And so tuning it in the field becomes more of a challenge. And so, and then to take that one step further, why don't we just put a neural network in there for the controller and just do some machine learning to figure out what the control system should be, right? And that's even more like removed from reality. It's super abstract. And at that point, you're like, oh, here's this table of 1 million numbers. It works in my model. Let me just throw it on my spacecraft And it just comes down to the point of like convincing yourself and other people becomes time consuming. And is that where you want to spend your time? So for me, it has always been build the simplest controller you can get away with that meets the requirements barely, because you're going to save so much effort keeping it simple. And there's a million problems you have to solve on an engineering project. So why are you, why are you saddling yourself with this really complex control law when you don't need it? Because you have to go off and figure out fault management and fault logic. And you have to go out and figure out modes and state machines. And you have to go figure out why your sensors aren't working right. And you have to go characterize your sensors. It's just like a long list of stuff that you just have to do. And so anywhere where you can simplify the system, the better.
So you mentioned modes, and that's something that I'm kind of interested in and learning more about. So basically there's different types of, I forget what the word is to say, but like different stages in the life cycle of a spacecraft. So say when you have your initial activation, you want to get initial communications
like phase
going. Yes. So can you talk about different modes? So say like the activation mode, and then maybe also a safe mode. So I don't know if this was the case in this kind of an extreme case, but say a solar flare is coming, or there's some other reason why you want to go into a safe mode, and what systems would you choose to keep on versus off in a safe mode, and then other modes like sun pointing, so I just want to charge completely all the way, or like earth pointing and that kind of stuff.
Yeah, there's a bit to unpack here. In some sense, you can interchange the word phase and mode and state. It is like a condition that the vehicle is in. And it's helpful to label a condition with something like activation, because it focuses you on what is important at this particular time and what can I ignore and shed, and what telemetry do I want to look at, and what things need to be on and off, and what are the requirements and all of that stuff. It's easy to sort of, it's easier to categorize various portions of the mission in that way, so that you can focus and think about requirements, all that stuff. So within ADCS, right, you look at the phases of the mission, let's say, with activation. Who knows what you're doing in activation? You're turning everything on, probably not everything, right? You may want to turn things on slowly, because this is going to be the first time you've actually powered everything on, and they're communicating with each other in a space environment. So, you don't want to flip the switch and just go crazy and be like, all right, go. Maybe you do if you've got a lot of confidence in your system, but if you don't have a lot of confidence, maybe you want to baby step your way in. There may be restrictions on activation. Like if you're a CubeSat, maybe you can't turn on until you've left the CubeSat deployer. Maybe you can't start transmitting until a certain timer has elapsed or something. So there's external requirements and internal requirements that you got to think about with each of these phases. Now, we may say a mode or a state also, and that might be like within like the activation phase of the mission. The spacecraft might go through several different modes, or may fault into a specific mode, for example. And again, it's the exact same question, is well, let's take fault, for example. What is the fault? Is it the check engine light come on? Is it low tire pressure? Is it, the smoke is coming out of my engine compartment on my car and it just stopped running, right? Each of those things are going to have a slightly different response, and spacecraft are no different, right? Is the current to my reaction wheel slightly high and troublesome, right? Do I need to shut down the reaction wheels because I'm worried that they are about to fail? Or does that high current just mean maybe I should desat because friction has increased more than I was expecting in like the lubricants, and so now I don't really want to spin these motors as high as I originally thought, so I need to desat a little bit earlier now. I can't store as much momentum. Or is is there a messaging failure or something? Whatever it is, right? You write all of these fault tests and you try to come up with all of these different ways that the vehicle can fail. And how do you want to sense those failures? And then you can say, okay, what if that happens? What should we do? Should we safe the vehicle? And that means something bad happened, but I'm not quite sure what. So let's go into a mode that uses the least amount of power, that uses the least amount of hardware and software so that we can keep this vehicle alive while we figure it out. And so with a reaction, with a ADCS system, that might be shut down the reaction wheels, shed all the momentum in the system with the torque rods, point the solar arrays towards the sun, stop using your star trackers because they take too much power, use the sun sensors, use the magnetometer, and use the torque rods or something. You know, who knows? It depends on whatever anybody comes up with for their particular system. But, you know, safe mode versus pointing versus whatever, these are all just ways that you want to operate your system, and it gives you a label to focus your thinking and determine what needs to work, what information do I want to have access to, and what do I want to protect against in this particular situation.
Okay. And going a bit of a different direction, I want to ask you a bit about orbit determination, because I know there's a lot of ways to do that, just like attitude determination. So in what ways did A3 and A6 go about that? Was it from the ground, just using the ground measurements in order to send the spacecraft, this is where you are, or was it more of an onboard calculating, where am I?
Yeah. So just like with any state estimation, like we talked about with the Kalman filter, is you can estimate your state with a model, and you can estimate your state with a sensor, and you can blend those two together. So with that understanding, we used two sensors for orbit determination. The majority, or the main sensor, was GPS, because we were at a low enough altitude that we could still use the GPS constellation. The other one was a measurement from the ground, from some tracking station on the ground, where they would say, this is your ephemeris. This is where you are at this time. You know, it's probably yesterday, but at this time, this is precisely where you were, and this is your state vector.
Do you get that from a TLE or another? Just
Yeah,
a state
well,
vector?
yeah, you can get it from a TLE, you know, through the government tracking programs and whatnot. You could also get it from, there's companies that just operate radar stations that'll ping your satellite and determine. You can get that state vector in any form that you want, whether it's, you know, position, velocity, and time, or TLE, or whatever. So those are the two ways for us to get an update, to get a measurement, which is like the update of our orbit, which is at this time, here's where we were and how fast we were going. From that point on, we would model where we were using an orbit model, like an orbit dynamics model. For A6, we used what's called SGP4, Simplified General Perturbations 4. This has been forever, by the way, so double check everything I'm saying. Which
that sounds right,
which
yeah.
Okay, good, yeah. Which was an orbit propagator that went hand in hand with like a TLE, and it is well, you can, I mean, you're better equipped to talk about this than me, but if you wanted to estimate an orbit, you could do so with like a simplified two-body problem, where you treat the Earth as a point mass, you treat the spacecraft as a point mass, and then, you know, what comes out are like these ellipses, perfect ellipses. Or you can give the Earth some volume, and you can say, oh, it's not a perfect sphere, it's kind of oblate, and so there's these like J2 perturbations that kind of mess with the orbit, and I want to take that into account. And then there's like these long duration effects from tides, and, you know, there's drag, and, you know, all sorts of things that can affect your orbit long term. And so depending on the fidelity of your propagator, you may choose different models over another. And the simplified general perturbations model takes those perturbations simplifies them, which is in the name, and comes up with what it is as a compromise between the speed in which you can do the calculations and the accuracy. And the way that we seed that model with an initial state on the vehicle was from a TLE that we would upload from the ground, or from a position and velocity vector from GPS, and then converted. I can't remember whether we converted the TLE into like position velocity or the position velocity into the TLE. But either way, we had to put them into the same coordinate frame because the GPS and the tracking stations on Earth produced state vectors in different coordinate systems.
Can you talk a bit more about how GPS works? Because I don't know too much about it, and I don't know how much you know about it, but I mean, it can get really accurate if you do it correctly from what I know. And then also, because I know at some point, if you want to say when you're on your phone and you're driving, you want to go somewhere, that those satellites have to take into account relativity in order to get very, very precise information. So can you just talk a little bit more about that, as much as you know from GPS?
Well, yeah, I don't know a whole lot. But I mean, they do take into account relativity. I mean, just from their clocks, right? They have to keep that, they have to, the whole thing comes, it's like a big time system. It's like a timekeeping system is essentially what it is. And if you know precisely where a bunch of every satellite is, and each satellite knows precisely what time it is, and it's all coordinated across all of the satellites, then it can send out these signals with a timestamp, essentially, and the ID of the satellite that it's coming from. And then your receiver can receive all of these signals, and it can say, oh, satellite 2, I just received its message and it sent it at time X, and satellite 3, I just received its message and it, and at time Y. And I know where those two satellites are because it told me. I can then triangulate, you need 4, but I can then triangulate where I am based on these, the time travel it takes for these messages to reach me. And it's, you can imagine that 4 satellites right next to each other versus 4 satellites spread out across the entire sky are going to produce different results, because the ones that are all clustered together are essentially going to be hard to there's not enough separation between all of them to get a good measurement, right? You'll know exactly how far away you are from all of them, but there's not enough in the other dimensions to get a good X and Y location. So there's this thing called dilution of precision, DOP, which come down or calculate. I can't remember. The GPS receivers calculate that. And so you can use this DOP value to determine how much you should trust your GPS measurements, because it is a value based on which satellites it's using and how spread out they are relative to you. So we use that in our state estimation. We use DOP to determine how well to trust GPS. And then satellites are moving really fast, right? I mean, kilometers per second. And so the cross-track axes, the ones that are not in the direction of travel, tend to be a lot more accurate than the in-track direction, because you're moving so fast and velocity needs 2 subsequent measurements to determine. And then you're like, well, I'll just average them and say that my velocity was at this time. And I don't know, it just gets a little bit tricky with timestamps and what to trust. So the error ellipse tends to get stretched out in the direction of travel. And you tend to not have as much accuracy in that direction. So, yeah, I don't know if I answered any of your questions there, but those are the extent of my, how we use GPS and the things that I was concerned with anyway.
No, yeah, definitely you did. So I want to bounce back a bit to soft sim and Monte Carlo simulations, because I think that's something that's pretty interesting. And then, you can go a lot of different ways as far as the software goes. So from your experience at Planetary, how were Monte Carlo simulations used, and then what were they useful for? Like, what kind of stuff were you looking for in doing these simulations?
Yeah, so a Monte Carlo simulation, well, let's say anything that has statistical variation. And so that might be, if you're building something, the length of a rod. Every time you build that rod, it's going to have some tolerance there that is, based on some statistics that, maybe it's normally distributed or something in some way. Same with everything else, like sensors. Sensors are going to have some amount of error. There's going to have some amount of bias, and that bias is not going to be the exact same every time you turn off and turn on the sensor. That bias is going to move. And how it moves is going to have some distribution, and it might be Gaussian, it might be uniform, it might be some crazy distribution, whatever it is, and so you want to ask yourself this question: I know my system, well, maybe you don't, but let's say I know my system works if everything that I'm predicting about it is right on, but everything has these statistical variations in it. And I don't know if my system is going to work if the bias on my star tracker is in one direction, the bias in my magnetometers in the other, the momentum of my reaction wheel is is a little bit high, and the torque that I can get out of my torque rod's a little bit low, and the time it takes to do my calculations is a little bit high, and all of that stuff, right? You want to vary all of these things according to their probability distributions. And if you can't do it mathematically, and what I mean by that is if you can't just like multiply two Gaussians together to determine what your new probability distribution looks like, what you end up doing is just sampling your system hundreds of times or thousands of times. And every sample, every time you create a new instance of your simulation, all of those variations are tweaked according to their own probability distributions. And so that as the number of samples goes to infinity, you will have simulated your system in every possible feasible configuration and that exists. Obviously, that's impossible. So what you aim for is enough runs to get a statistically significant swath of the entire state space. And so that's essentially what a Monte Carlo is. A Monte Carlo is setting up your system to run over and over and over and over and over again, with each time being initialized in a slightly different state, but a state that has some probability of it being in there. And then let's say you run 1,000 times, you can look across all of those and say, did I meet my pointing budget across all of them? And more often than not, you're going to say, no, out of 1,000, I missed three times. There's 3 configurations out of 1,000 where I miss my pointing budget. Well, that's where the statistics come in on the requirements, because the requirements might say, I need to meet 1 degree plus or minus 3 sigma. And what that's saying is like, or 1 degree of 3 sigma. Basically, it's saying like 3 out of 1,000 times, it's okay that I miss that, as long as the other times I'm within, I'm within my requirement. And so that's what Monte Carlo is good for. It allows you to set up your simulation with all the probabilities of everything that you think, and then just brute force run through a whole bunch of different variations and get statistics on how well your system does.
So as long as you have good enough models for all your systems, all these kind of statistical variations of every single component of your system, you can create kind of, as you said, like a brute force state space where you say this many times out of this many times. And is that enough to be able to convince a whole team, or to go forward with a design that says this system will work to this percentage of certainty?
Well, sure. I mean, it's the same as anything, right? It's model-based design. So it's only as good as your model. And so the majority of, if you have to go off and defend your design, if you do model-based design, a lot of your defense is going to be in defense of the model. And you're going to say, here is why I trust this model. I compared it to this physical hardware in this situation. I compared it to this peer-reviewed paper in this other situation. I compared it to what Project X did last year, whatever it is. And you're like, I've gained trust in this model. Here are the parameters I varied, and these are the statistical distributions that I chose and why. Here are the parameters I didn't vary because I, for whatever reason, I did a sensitivity test on this one parameter, and it didn't seem to impact the design at all. So I've ignored that. This one isn't on in this mode, so I've ignored that, right? And you just like set up a defense. You just say, here's why I trust my model, here's what I did, and then here are the results. And this, you know, and then you get peer reviewed in, right? You get external auditors or people that you know what they're talking about and haven't been involved in it day in and day out to come in and say, oh, but did you think about this? And then you say, yes, I did, or no, I didn't, or whatever. And eventually, you know, you've convinced yourself and some, you know, independent auditors or whatever it is that your company or has decided to do, you know, to gain trust. But Monte Carlo is no different than model-based designing your control system to begin with, right? It's do you trust your model? And if you do, then essentially all you've done is run your model 1,000 times.
It's kind of the balance of knowing, so say you do a lot of work in Simulink and MATLAB, so the balance of knowing all that Simulink and MATLAB versus actually knowing what's going on underneath the hood, because they're both very high level languages that you use as and just like Python versus as opposed to say a C or C++ or Fortran. So kind of that relationship between being able to work very proficiently in Simulink and making these very complex models versus actually getting into the weeds of knowing what's going on as to actually how it's being implemented into embedded software.
Well, I think it comes down to where you want to spend your time. I'm not a software engineer, but I would imagine that if you could include a library of functions that does what you want to accomplish, that's going to be preferred, especially if that library has already been vetted and used and documented. That's going to be preferred over writing your own code from scratch in a lot of cases. I mean, sometimes libraries don't exist and you have to write from scratch, or you're doing something highly specialized, or you don't want all the bloat that comes along with, you know, some kind of built-in function. But for the most part, you want to reuse things that have already been created. And reusing something shouldn't preclude you from understanding it. It just keeps you from having to write it yourself and keeps you from making the same mistakes that everybody makes whenever they do anything, right? You just, you know, they don't understand, they forgot to include something, they made a typo, whatever. And so it just saves on time there. But I wouldn't advocate anybody include a library or something else that was already written without understanding what it's doing. And so now when we get to MATLAB and Simulink, I think of them as libraries of algorithms and an ecosystem that allows you to connect them and simulate them and visualize them and generate embedded code from them in a way that is simpler. Like, you don't have to spend as much time doing it as you would if you did it, you know, yourself, you know, from scratch in some way, and it keeps you from making those kind of same mistakes. But I wouldn't advocate for anybody connecting blocks in Simulink and writing in some MATLAB code and functions without understanding what's going on underneath it. You can absolutely do that, right? But you can do that with anything. You could, you know, put a bunch of numbers in Excel, highlight it and say, plot a linear line and give me a linear regression, give me a best fit line. And you can run off with it and you could be pretty successful with it. But if your job depended on that answer, I would spend a little bit of time understanding, what is this thing even doing? You know, what is linear regression, and understanding it. And that's what I would advocate for using MATLAB and Simulink. Also, it is a fantastic tool and it's a fantastic set of libraries, but it shouldn't be used like blindly, because you can get yourself into trouble if you just say, oh, this is a 3 degree of freedom block, let me just pull that in and move on, because you don't quite know what it's doing, all the information is there. You can find out. It's not like a black box. But it just keeps you from having to write all of that stuff yourself and research everything. You can read all about it and know exactly what it's doing and figure out whether that is what you want to apply to your situation. But you're still going to understand what it's doing.
And then going off that, can you talk about a little bit of the trade between using the Autocode feature of Simulink and MATLAB versus, say, hiring a bunch of embedded software engineers who could also write that software and maybe interact with the controls engineers who are writing, say, control laws, or just the general architecture of the flight software, kind of where that trade goes and when you want to rely more on, say, an Autocode versus hiring a bunch of embedded software engineers?
Yeah, I haven't given much thought into the trade outside of ADCS. So this isn't a general statement. But from my experience, being, control systems, ADCS, GNC, all of that stuff is a specialized field. And you can get the basics pretty quickly, but there is a lot of just of experience and breadth to this field that you have to know and understand in order to not sort of fall into the same pitfalls that people have been falling into for dozens of years. You can learn from them and not do that. And in order to learn from all of that, it just takes, some experience and study and things like that. Same for embedded code, right? Embedded code is a complex field. Like you could probably write some code pretty simply that, does hello world or whatever, runs on the embedded processor, but you don't know if you're missing any best practices, for example, that people have learned dozens of years ago, and you're just falling into the same trap. It requires a lot of expertise. If you can find people that have both of those expertises, that's amazing, and you should do that. And you could save you a lot of heartache, probably, to have the same person design these complex algorithms and then embed them into the flight software, write it themselves, do all of those testing. But there's also some really fantastic ADCS engineers out there that don't know code, like me. I consider myself, I guess, fantastic, but terrible at code. And then vice versa. There's some great embedded code software engineers out there that don't know enough about ADCS. And so it's like, okay, well, how do I bridge that world now? How do I capture the knowledge of algorithms and ADCS knowledge from one group and apply it to this other group that's actually doing the coding? And at Boeing, at least one of the projects I was on, we did that by writing what's called algorithm description documents, which were just massive volumes of block diagrams and text that described what we wanted done in minute detail. And we would take that ADD, that algorithm description document, and hand it over to the software team, who would then read through it and code it all up. And it was terribly inefficient because we may have designed a perfect algorithm, but described it poorly. Or we may have described it well and they interpreted it poorly. Or they interpreted it well and we tested it poorly. All of a sudden you've added all of these places in there where error can creep in. And so that's where Autocode can be nice, because it allows you to take the expertise of the person developing the algorithm, the capabilities of the software to develop to generate embedded code from that, and then the expertise of the embedded software team to wrap the rest of their flight software around it. Now they don't have to be algorithm experts. They can take those algorithms, take it out. They don't even have to use the entire embedded code. They can take those functions that were generated and then just stick them into the embedded code that they're writing, and they know all of the nuances and the details of hooking all of that up, but they don't have to be experts in the algorithm itself. And now those two teams can work closely with each other, with one developing essentially the source code in MATLAB and Simulink, if that's what you're using to do your Autocode, the other one building flight software, and then you can get together to test it and say, hey, here's what my flight software is coming up with. Now, does that match what MATLAB and Simulink was showing? And you can say yes or no and troubleshoot. And then once you get that handoff done, then it's relatively easy to just make changes on the Simulink side, Autocode, pull into the flight software, and you're off and running. And it's a nice way to bridge the expertise of these two groups without requiring these highly specialized employees that are experts in both.
Transition into your videos. So in the early days, first of all, what prompted you to start making videos in the first place? Yeah, because I don't even, that was a really long time ago. So yeah, so I guess way back then, what was your initial
It's making me seem
decision?
old.
What was that? Yeah, go ahead.
Go for it, sorry.
Oh, just what was the kind of motivation that says, okay, I wanna teach people, I suppose, or
Yeah, well, I've always enjoyed teaching, so that's been around forever. And I always thought I would go into industry for some amount of time, learn a bunch of stuff, and then go off and teach. I didn't think it was going to be like this, but the genesis for my videos actually came when I moved up to Seattle with Boeing. My cubicle, like next door cubicle mate, was a man named Monte Evans, who worked 777 flight controls for a long time and was just really smart in understanding control theory, specifically frequency domain classical controls, which I had very little experience with at the time. And I lucked out because I was right next to him. And not only was he really, really good, he had a good intuitive grasp on things, and he liked to answer questions. And so I would have a question for him, and then he would come over and he'd write it down, and he'd say, oh, you got to think about it like this, and it makes more sense if you do this. And I remember thinking, man, this was such a good explanation. If I just had that, the math would make a lot more sense, right? Like, I spend so much time trying to learn this math without having a good understanding of what it was before I got into it. And so I thought, just for my own sake, it wasn't intended to be this big thing on YouTube. Just for my own sake, I wanted to kind of walk through a few concepts in the style of Monty, of how he explained it to me, where I set up the problem not from a mathematical perspective, but just from an intuition perspective, and say, this is what we're doing, and this is why it makes sense, and what it all means. Now you can go off and read the textbook, and hopefully it'll all make a little bit more sense, right? Not go into the math, just stay with the intuition. And I made a couple videos, and then I got comments that were like, I got like 11 views or something, which was amazing. And I got a few comments of like, hey, I'm looking forward to the next one. And I was like, well, I hadn't considered a next one, but maybe I will. And so for the first year or so, comments really drove me to keep making more. I would talk with Monty and other people, and I'd kind of craft a story, and then it just sort of took off from there. It was always a hobby. It was always something I would do on nights and weekends or something to come back and fiddle around with videos. Oh, this was great. Yeah, thanks for inviting me on, for sure, and putting sort of some trust and faith in me for your first guest. This was good. I enjoyed it. I enjoyed talking. Hopefully some people will find this and get some value out of it. And if not, hopefully you get to springboard on this and talk to some more people and continue, because I think this is great. It was fun to talk about engineering, and it's easy to talk about your own experience, right? It doesn't require too much prep work.
Right. Yeah. And yeah, as you said, the worst case, no one watches it, and then I get to talk to a bunch of smart engineers. So it's,
yeah.
Win-win.
Well, I'm gonna